We are about to launch into week 3, and in week 3 we're going to be considering some very interesting connections between pressure and a variety of other phenomena for the Earth. And what we really want to emphasize is that pressure is a rise from matter and that pressures really matter. So we'll have some fun with this and make some connections. Really what we want to do is even more ambitious. We want to set the stage for understanding these energetic fluid motions that are part of the Earth, the motion of the air, the motion and circulation of the water, see how these things are connected. And we want to really be as efficient and as effective as we can to see these ideas that are shared by a wide variety of applications. Really, if we can be as lazy as we can, we want to seek the largest bang for the explanatory buck. We want to see if we can really connect things together and make these connections. And in fact, something that we won't have time to do here, but something that we challenge you to do, is that these connections are even vaster than what we're going to see for the Earth, that they relate to the universe as a whole, that the basic ideas that we'll talk about of a differentiation between light and heavy materials, between the way gravity separates things, the way energy is flowing when we condense things and when we lose them when we have an expansion process, that this relates to the universe as a whole and not just to these energetic phenomena for the Earth as a whole. So that's the overall goal. What we're going to try to do, though, is build things up quite systematically and try to keep the ideas fairly simple. So really encourage you to hang in there and try to work with us, see how one idea leads to the next idea, and that we very much hope that you'll find that this is worth the effort, that what we're going to link together is really quite marvelous. And we hope that you'll stand back and marvel at these explanatory power that we have in these simple ideas. So that's our goal. Let's going to jump in now and see what links these together. We're going to start off with a very simple idea, the idea of hydrostatic pressure. Pressure, to remind you of that, is a force that acts perpendicular to a surface. We can create those surfaces within fluids in a variety of ways, and it's expressed on a per unit area basis. A typical unit is that we might have newtons per square meter of cross-sectional area. Newtons is actually a very small force, and so often we're going to be working with things like kilonewtons or even meganewtons per square meter, or sometimes even giganewtons per square meter. This Newton per square meter is sometimes called a Pascal in honor of one of the great physicists that studied this, Blaise Pascal, who made contributions in a variety of different areas. Statics comes from the Greek word of statikos, which means motionless, and these fluids at rest play a key role in terms of driving this overall process. If the fluid is going to be at rest, it can't have any forces along the surface that would induce the fluid to move. And these forces along or parallel or tangential to a surface are called shear forces sometimes. Sometimes that's a bit intimidating. We talk about those shear forces. It sort of has that idea of tearing along surfaces. And if shear forces were to arise, the fluid would flow. Fluids can't resist such forces. And so those forces must be absent if the fluid is to be static. And that means that any surface that we create, this small box that's going to contain fluid in our mind, has to have these pressure forces acting on it, and these pressure forces are going to act on all surfaces. And in fact, one of the key results that we get is that in a hydrostatic fluid, so we don't have any of these shear forces, that the force must act equally in all directions. That may be a bit of a surprise to you, but hang in there again. We're going to show you some animations in a minute or two. Those animations will show you that, in fact, you probably understand this concept better than it might appear that you do when we express it in this somewhat mathematical or abstract way. And if there were shear forces, that we would result in imbalance, and if they weren't equal, result in imbalance, and we couldn't have a static fluid. And so that's the basic idea of what arises here. In order to make the link that we really want to do, we want to link pressure and weight through gravity. And I think the easiest way to imagine this is hopefully to recapture your imagination and experience that you probably have when you've at some point made a dive into the water. And at that instant of crossing that boundary of the liquid fluid engulfing your body, you'll have a dramatic change in your experience. The light, the sound, the temperature, the heat, the weight, all of those things change across the boundary. If you jump into the fluid in the summertime, then quite likely the fluid is going to be colder, and you'll instantly feel the difference. You'll hear the difference. You'll sense the difference. And what, if you're at least bit attuned to that at all, is you'll sense that there's a dramatic change in the fluid pressures as well. Hopefully you're not going to panic, but there may be a significant change in your mobility and your sense of control and your experience of gravity and a variety of other things. But your ears, if you dive in, will instantly notice and easily notice that there is going to be a rapid buildup of pressure. And you might ask yourself, well, what does that reflect? What does that build up of pressure respond to? And that the answer is quite easily understood, that there's a weight accumulation. And in fact, the weight of the fluid above you is accumulating very rapidly because that liquid is much heavier than, or much more dense than the air above it. About 800 times more dense in the case of air to water transitions, and that results in this huge difference. And we'll show you an animation in just a few minutes that will help you to visualize that, but let's just walk you through some of the key things here. The second thing to add to our mixture is that these forces, these static pressures, really matter. There's all sorts of crucial implications, and we've extracted just 7 of them for your instant education at this particular point. First of all, the forces that are accumulating have great significance to engineered systems. That the buildup of those pressures are sufficient to allow things like pipes sometimes to burst, or for containers to crack if we push them into the ocean too much. We can have leakage in a submarine or in a pipe, and even our eardrum can fail if we fail to equalize those pressures. If you ever dive into the water, and in particular if you've got a cold or a sinus infection, the force on the eardrums, even for merely going a few centimeters or a meter or so within the water, can be quite excruciating. It also, of course, has implications for access, that really large pressures and large forces are hard to withstand, and so it means the deep parts of the ocean are hard to get to, and humans only get there infrequently and only with a great deal of preparation. Within the surface of the earth, deep mine shafts or deep wells or deep oil investigation wells are extraordinarily expensive, and so the accumulation of this weight of the fluid above us, or of the surface above us, creates an access problem as well. Not only that, but there are other changes that are induced by these buildup of the pressures. The buildup in the pressures can cause chemical reactions, it can cause phase changes, and they're ultimately the source in the accumulation of these pressures and temperatures that cause volcanoes and induce the formation of magnetic fields, cause plate tectonics, and all sorts of interesting subsurface phenomena that are often associated with the pressure and temperature buildup as a result of the accumulation of that process. Certainly when air expands, when we lift air above the surface, that expansion process has to be paid for energetically, and it typically causes the expanding air to cool. And the reverse process takes place when the contracting or descending air or water takes place on the surface, and we cause a warming effect that takes place as well. And in fact, this warming effect can be so profound and the pressures can be so great that in fact not only do chemical reactions take place where we overcome the normal boundaries of atoms, and we cause reactions to take place between atomic species, but we can have nuclear reactions taking place as well, and stars can ignite and nuclear reactions take place as a result of the vastness of the accumulation of weight that takes place within a star system. One of the things that's significant as well, though, is that flow takes place, and even quite small pressure differences can cause flow to occur. And these pressure differences arise and cause circulation and winds and change and currents as a result of these changes, as we'll see soon. And humans care about these things, certainly engineers and economists do, because we often have to pay for fluid pressure differences to take place, particularly when we have to run pumps using electrical energy, or when we sometimes recover that pressure through things like turbines and can generate power. So these are some of the significant things. This is kind of a overall list, a summary. We will see these things come to bear as we move forward. The basic idea that we're talking about here, though, is that when we move down in a liquid, this is the kind of liquid that we can imagine diving into again, that we have a buildup of the fluid above us, and that fluid has to be supported. Otherwise, the contraction or the compression would continue, and that supporting force is, in fact, the pressure. The pressure, as we go deep within the fluid, represents the accumulation, the weight above us. And there is a way that we can give an expression for that. There's an equation, but the equation is simply stating that the rate of change of pressure with height in the static fluid exactly equals this property of the fluid called its specific weight, or its weight per unit volume. The expression is this little equation here. If you don't have a math or a physics background, then don't worry about the equation. But it basically says that pressures change with height as a result of this fluid property called this specific weight. If we go up, the pressures go down. If we go down, the pressures go up. So this Z is taken as vertically upward or radially away from a planet's center of gravity.